Hey folks, in this video I'll show you just a few examples of integrating using polar coordinates. So for the basics, you can review what we did in class, check out the video, but here we'll continue that discussion. So let's start with this question that you may have seen on the worksheet. What's the volume between the graph of this function, 1 minus x squared minus y squared, and the xy plane? Well, we might start by asking, what's the region of integration? Remember 1 minus x squared minus y squared, this is a downward facing paraboloid. So the region of integration will take place sort of inside that bowl. So we can start by looking at where the bowl actually intersects with the xy plane. Well, the xy plane happens at z equals 0. So if we substitute that into the equation for the paraboloid, we can solve and see the intersection happens on the unit circle. So that's our region of integration. We want to know the volume basically above that footprint of the unit circle, but still under this paraboloid. So we can write down our double integral. And well, I think you'll agree that the x coordinates, these take place between x equals -1 and x equals 1. These are the sort of left and right bounds of that circle. But if we were slicing it vertically, then for each vertical strip, the bottom will take place on the lower hemisphere of the circle, the top on the upper hemisphere. We can write those in terms of y just as the positive and negative square roots of 1 minus x squared. So we'll put the paraboloid function in as the integrand. Not so bad so far. We can anti-differentiate with respect to y. But then we would plug in these square roots for y, and then still have to integrate with respect to x. I don't want to do that. So you can try it if you'd like. We'll see what the answer is on the next page. You can check your work. But let's see how we would do this using polar coordinates. So first, remember our polar version of Fubini's theorem. That is how we can write a double integral as an iterated integral using r and theta. So we'd have r bounds, theta bounds. We write our function f using the variables r and theta rather than x and y. And then when we replace dA, we write r dr d theta. So we get this extra factor of r that we can't forget. So to see how it looks, for the region from this question above, remember it was the unit circle. Well, if we want the whole unit circle, we need theta to go all the way around. So that's from 0 to 2 pi. The radius of the unit circle is 1. So if we want everything inside of it, we need our r bounds to go from 0 out to 1. And then this function 1 minus x squared minus y squared, we can write as simply 1 minus r squared. So you can think about why that's true. If you'd like, you can plug in r cosine theta for x and r sine theta for y, and then simplify. Or remember that r squared is x squared plus y squared. And then dA, we replace that with r dr d theta. And this is much more manageable. We can distribute that r. We can anti-differentiate with respect to r. Plug in the r bounds, 0 to 1. We can anti-differentiate with respect to theta. Plug in the theta bounds, and we see that our answer is pi over 2. So much, much nicer. We didn't have to deal with any of those terrible square roots in the integral before. You could do it. You would need to use trig substitution. I'm not interested in doing that. So let's look at a few more examples. I don't want to compute any more integrals, but let's just write down what these iterated integrals would look like using polar coordinates. So in this particular example, imagine our integrand is simply the function x. And well, this first region is sort of this quarter donut. Well, the theta bounds, this is happening in the first quadrant. Theta is going from 0 up to pi over 2, and then we stop. The r bounds, we're going from sort of inside radius of 1 to an outside radius of 2. And then for our integrand, well, we want to write x in terms of r and theta. Remember, x is r cosine theta, so we'll plug that in there. And then we can't forget that extra factor of r before we write dr d theta. So that's what we got. The next one, this semicircle. Well, we need theta to go from 0 all the way to pi, so we get the top of the circle. And the r bounds here, well, there's no hole in the middle, so r should start at the origin and go all the way out to the perimeter of the circle. That is, we need to go the full radius of 3. And then finally, this last one is a little tricky, but we can handle it. Here we've got a circle of radius √2, but we want just sort of the cap. Notice this shape has its endpoints at 1, 1 and minus 1, 1. We could check that this angle in the first quadrant is pi over 4. And then you can imagine by symmetry what that angle to the last endpoint would be. And in terms of the r values, well, the outer radius, that's √2. It's a circle of radius √2. But this inner, well, I'll call it an inner radius, this straight line, is given by the equation y equals 1. But we know how to write y in terms of r and theta. Y is r sine theta. So we'll write r sine theta equals 1. We can solve that for r. And now everywhere in that region, there's an outside or like upper radius bound of √2, but an inside or lower radius bound of 1 over sine theta. So we'll put that in there with our integrand r cosine theta times the r we get from dA. That's what we've got. So take a look in the textbook to try some more examples of this, and I'll see you soon.